The fundamental theorem of algebra says that every polynomial has a complex zero, written as x minus c, when it is equal to 0. So this is a polynomial function. We know by the fundamental theorem of algebra that this does have a complex 0 when it's equal to 0. What is it? Well, we can factor it and see. If we factor this thing down, we can take out a 5. So 5x cubed minus or plus 27 equals 0. This is a sum of two cubes. If you don't know the breakdown for that, I recommend you look it up. This can be factored into x plus 3. The 27 is 3 cubed. And then x squared minus 3x plus 9. And we can see that this does in fact have a 0, a complex 0. The complex 0 is just -3. Real numbers are complex numbers. So it does give us that x equals -3 is a complex 0. I can write it in this form by just saying x plus 3. That's the complex 0 that it's looking for. This and this. However, I can ask the question again. This is a polynomial function. I can write, g of x equals x squared minus 3x plus 9. This is a polynomial function. And by the fundamental theorem of algebra, this must have a complex 0 in it. In this case, I have to use the quadratic formula. I will get negative b plus or minus b squared minus 4 times a times c all over 2 times a. Okay, that's going to give us the square root of -27 over 2. Square root of -27 is just 3i over 2. So in fact, we get two complex numbers from this, and they're conjugates. And I can write it out as a complex 0 as x minus 3 plus 3 root 3i over 2, and x minus 3 minus 3 root 3i over 2. And now you can see that this and this are also these complex zeros that the fundamental theorem of algebra says are there. And this gives rise to the idea, well, that whenever you factor anything down, you have another polynomial, and so you can use the fundamental theorem of algebra again. And this idea of continually using the fundamental theorem of algebra, this is what gives us the linear factorization theorem. A polynomial of degree n has n complex linear factors. You can factor it down completely. This is a degree 3. We found 1, 2, 3 zeros from it, three factors from it. And that's the key thing to keep in mind is that whenever you have a degree n, you always are expecting n complex linear factors. Now those factors may be repeated, and that is where the multiplicity comes into play. But it doesn't matter. You're going to be able to count up n of them. So if it's a quadratic, you should expect 2. If it's a cubic, you should expect 3. If it's a 15th power, you should expect 15 factors, 15 zeros total. So go ahead and give it a try in number 5. Okay, how can we solve this polynomial equal to 0? How can we solve this? Well, for a quadratic, we have the quadratic formula, which I just showed. And there are actually cubic for cubed functions, and there's actually quartic for a power of 4 degree formulas for these. But these are actually, I recommend looking them up. These are hard to use. Give it a try on something for yourself. I've never used them because they're pretty much prone for error, but they are available. However, we don't want to use them if we don't have to. We can actually do something different to solve for the zeros. And to do this, we need polynomial division. And that allows us to find zeros for higher degree polynomials. We do this operation, this polynomial division, so that the power goes from, for instance, 4 here, it'll go to a lower degree. Whenever you divide out something, it reduces the power. And if we can reduce it down to a square, for instance, the quadratic formula is quite easy to use and maybe easy to factor. So that's the kind of goal that we're doing here, is we're going to factor it down as far as possible. Now, in the actual process of division, it follows a lot the same as long division. We're really just going to be doing the same process, except there's just different things that we're working with here. So first off, I'm going to write this in the right form, and I'm going to write the first part, which would be in the numerator. This is going to go underneath the bar, the long division bar. And I'm going to write in every power of x from the highest power, the degree is 4, all the way to the lowest power. So you can see here, there is no x squared in this. I'm going to add that in by adding a 0x squared, then minus 7x and minus 6. I've gone from the highest power to lowest power. Always write it this way. I think it's going to be easier to make sure you've done it correctly. The divisor, the denominator, goes on the outside. And now we can do the process. We look at the first term from each of the polynomials and divide them. X to the 4th divided by x squared is x squared. That number that you just found goes on top. And now we can multiply this thing into this polynomial here and write it underneath. So x squared times x squared is x to the 4th. X squared times x is x cubed. X squared times -2 is -2x squared. If the columns are not lined up, then that means you've probably written it wrong or you've missed something, because you should expect the 4s to line up, the 3s, the 2s, and so on. Then at this point, we're going to subtract. So what I'm doing here is really the same thing that you would do for any kind of division. I'll show you a very simple one here. For instance, 687 divided by 4. We can go 687 divided by 4. 4 goes into 6 how many times? Well, 6 divided by 4 is 1 with a remainder of 2. 1 times 4 is 4. Subtract, we get 2. Then bring on the next one and do the process again. This is actually the same process we're doing here, except it just requires a little bit different algebra in the polynomial division. Okay, now x to the 4th minus x to the 4th, or we're going to always subtract just like we subtracted here. This gives us a 0, and you should always expect the first column to cancel. Then 2x cubed minus x cubed is 1x cubed. 0x squared minus a -2x squared is plus 2x squared. Bring down the next term and then restart the process. The first term in this polynomial divided by the first term here gives us x. That goes in the numerator, or sorry, in the answer. And then we multiply x back through this divisor. X times x squared is x cubed. X times x is x squared. And x times -2 is -2x. Now we subtract. We get 0 again in this first column. Then we get 2x squared minus x squared That's going to be just x squared. Negative 7x minus negative 2x. That's going to be plus 2x. It's going to give us negative 5x. Bring down the next term, and we can continue. Divide the first two terms together, x squared over x squared. So we get 1 times x squared is x squared. 1 times x is x. 1 times negative 2 is negative 2. Subtract, once again, we have 0 here. Negative 5x minus positive x is going to be negative 6x. And then negative 6 minus negative 2 is plus 2, so we get negative 4. And this is where we can stop, because x squared cannot divide evenly into negative 6x. This needs to be at least an x squared for us to divide the two of them. So this is our answer. We have this portion plus the remainder over the divisor. Let me show it like this. That's going to go down here. And that's our final answer. So this x squared plus x minus 2 did not divide evenly into x to the fourth plus 2x cubed plus 0x squared minus 7x minus 6. If it did, the remainder would be 0, and this whole thing would go away. In this case, it did not divide evenly, so we have a remainder, and that's how you can write it. Okay, let me show you another one. Let's write the this first portion is in the numerator, so that was going to go underneath the bar. And this is the divisor, it's the denominator, so that's going to go on the outside. Okay, so first term and first term, 6x cubed divided by 3x is going to be 2x squared. And then multiply it through. And give us 6x cubed plus 8x squared. Subtract. We get 0. Again, that's what you expect. 17 minus 8 is 9x squared. Bring down the next term and continue. 9x squared divided by 3x equals 3x. Multiply 3x through here. 3x times 3x is 9x squared. 3x times 4 is 12x. We get 0 from the first column. 27 minus 12 is 25x. Bring down the next term and continue. 25x divided by 3x equals I found my error here. I actually made an error. 27 minus 12 is 15, not 25. 15 divided by 3 is 5. Now, I don't know if this will always be an even number. I think it actually can be a fraction quite easily. Most of the problems that we deal with when we're doing this are going to be even numbers like this, but just be aware that there could be a fraction here, and then you just put a fraction up here. It'd be plus like 5/3 or whatever up there, and then you just multiply 5/3 into here and then continue. In this case, it's just 5. 5 times 3 is 15x. 5 times 4 is 20. And subtract, and that gives us 0 and 0. And this is what I wanted to show, is that this 3x plus 4 divides evenly into 6x cubed plus 17x squared plus 27x plus 20. So our answer is just this portion here, 2x cubed, or sorry, 2x squared plus 3x plus 5. There's no remainder, so there's nothing else to write with a fraction like we did in the first one. Okay, give it a try in number 6. Now, there is actually a faster method to divide polynomials, and that is using what's called synthetic division. The only way synthetic division works is if you're dividing some polynomial by a linear factor x minus c. If it's not in this form, you cannot use synthetic division, so keep that in mind. Now, this one here, this is actually the number 6, so I'll show you how to use that in synthetic division. I'm going to add in the zeros that are missing, so I have a 0x cubed to add in and a 0x to add in. I made a mistake. There is an x there. It's the regular 0. It's plus the 0 that goes on the end at the end that I'm missing. So that's what I have here. I have this top thing with added zeros, 0x cubed, and then the 0 at the end. And then x minus 4 goes on the bottom. Now, the x minus c is the thing that we're going to keep in mind here. And x minus c here, if we have x minus 4, that means c equals 4. Okay? And this is how we do synthetic division. I'm going to create this little diagram here. I'll put c in here in this box. And then I'm going to write all the coefficients along this top row that I'm going to create. So 4, 0, -4, 6, and 0. And then draw a line like that. So we're going to add going downward. So here we have 4 plus nothing is 4. This first one always is just going to be plus nothing. It's going to be the same thing. And then we're going to multiply by c, or in this case 4 going up. So this is 4, so we're going to multiply by 4. 4 times 4 is 16. Add going down, 0 plus 16 is 16. Multiply by that c value, which is 4 going up. 16 times 4 is 64. Add going down, we're going to get 60. Multiply going up by 4, so 60 times 4 is 240. Add going down, 246. And multiply by 4 going up. That's going to be 984. Finally, we add going down. 984 is our remainder. The nice thing about synthetic division is that not only is it faster, it actually gives us the answer right off the bat. I'm going to remove these, multiply by 4, just to make it a little bit easier to see what I'm talking about. Is that all I have to do is start with this term here, 246, and then go plus, and then add an x, then go plus, add the next power of x, plus add the next power of x. So our remainder is 984, and the remaining polynomial that we get from this division is this one here, 4x cubed plus 16x squared plus 60x plus 246. If you did the exercise here with doing the long division, then your answer you got from that should have been 4x cubed plus 16x squared plus 60x plus 246 plus 984 over x minus 4. So we got the same answer using long division or synthetic division. We can use synthetic division, however, because it was in this special form. Now, by the linear factorization theorem, all polynomials reduce into factors x minus c. And it just so happens that synthetic division only works for factors x minus c. So we can use synthetic division to remove these linear factors from a polynomial to find all of the zeros for it. That's actually how we're going to solve this polynomial here. Now, I don't have any other information from it. I don't know what to factor first from this thing to find all the zeros, because really that's what we want to do is we want to factor it. It's the same thing as asking what are the zeros. So factor is the same thing as asking what are the zeros. One's an algebraic thing equal to 0, the other one's the graph. And so where do we start? Well, we start actually by graphing this thing. So that's what I've done here, is I've just graphed it. The y-axes are a little bit weird because this thing is very tall. But you can see I just graphed this function, and now we're going to just use Desmos, and it tells us that it has 3 real zeros here: -4, 2, and 5. So we found 3 real zeros. You can zoom out far enough and you're not going to see anything else. Like there's no zeros hidden, if you zoom out, there's no zeros hidden over here or anything. These are the real zeros that are actually on this graph: -4, 2, and 5. However, we know that this graph has 5 zeros total, which means if there's three real zeros, there has to be 2 more complex zeros. So -4, 2, and 5. So it has zeros at -2, 4, and 5. All we need to do now is find what are the remaining 2 zeros. And how can we do that? Well, if it has zeros at these 3, that means that's the same thing as saying this polynomial has factors x plus 2, x minus 4, and x minus 5. Because when this equals 0, you get x minus 2. This one gives you x equal to 4. And this one equal to 0 gives you x equal to 5. Well, these are each linear factors in the form of x minus c. That means we can divide them out of this polynomial and use the linear factorization theorem to find all 5 zeros. So we're going to go ahead and do that. The synthetic division for this one is going to be, I'm going to start with -2. -2 is my c, so -2. Then the coefficients of this polynomial are 1, -7, -1, 97, -250, and 200. Now, because this is a 0, that means that when I do this synthetic division, I expect there to be a 0 here. If there's not a 0 here, that means I've done something wrong with my synthetic division. I can see, well, if I look back down my 0, I have -2, 4, and 5. And of course, I flipped the negative on the 4 and the 2. So it's actually -4, +2. So I'm going to write -4, +2. So the zeros are going to be x plus 4, x minus 2. That's going to be -4, and then recontinue. Add going down, we get 1, multiply by -4, -4. Add going down, -11 times -4 is +44. Add going down, we get 43. Multiply by -4, it's going to be -160, 172. Using a calculator, 97 minus 172, -75. Multiply by -4, 300. That gives me +50. Multiplied by -4 is -200. Add going down, that gives me 0. So you got to be careful with your work. It's very easy to make a mistake in this process. Now, instead of having to rewrite this whole thing, the nice thing about synthetic division is that we can continue using what I've already written. The next 0 we want to remove is 2, so I can just write 2 here and restart the whole process. We're not going to use a 0, that's just a 0 for the remainder. We know that 2 is a 0 of this polynomial, so I expect a 0 for remainder. And going ahead and doing the process, add going down, multiply by 2. 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 And we get 0 for remainder. So I've done that one correctly. Last one to remove is the 5. So let's go ahead and do that. 1 plus 0 is 1 times 5 times 5 times 5. And you can see we get 0 again, which is what we expect. So our remaining polynomial is 5 plus negative 4x, and then 1x squared there. And we know that this thing has 2 zeros because it's a quadratic. And how do we find them? Well, we can use a quadratic formula to find the last ones. So we're going to have x equal to negative b, it's going to be 4 plus or minus b squared is 16 minus 4 times a times c is 20. All over 2 times a, that's 2 times 1. So we get 4 plus or minus 2i over 2. Dividing that out, the 2 out, we get 2 plus or minus I. And there we go. We have our 5 factors. I can write this thing in completely factored form, h of x equals the 3 factors we already knew, x plus 4, x minus 2, and x minus 5. And then we have x minus 2 plus I and x minus 2 minus I. All of these are in the form x minus c, and there's 5 of them. That's what the linear factorization theorem has told us. It's a 5th degree polynomial, so we expect 5 linear factors in the form x minus c. Now I should note that you can also have some number in front, some a in front, that will shift it in some way. That could be what happens in your polynomial. That depends upon whether or not there's some number in front of the leading term. But it doesn't really matter whatever that number is. Whenever you factor it, you expect there to be 5, in this case 5 linear factors, as I've written here. That number in front doesn't change that fact. Okay, give it a try in number 7. So the last thing I want to look at here is that synthetic division only works for these polynomials to divide them, of course. But what it's actually doing is it's actually finding the function's value for p of c. So if you plug in this value into the function, that's what synthetic division does. And if you get a synthetic division that gives you 0 as a result, that means p of c equals 0. That is a 0 of the function. It's an x-intercept, which is exactly what we were looking for. For some long polynomials, this can be easier to use rather than a calculator because you have to type in all the powers. But it's kind of up to you. I'm going to write this one. I'm just going to show you it. Q of negative 4 is the same thing as, let's see, we're going to take 2. We're missing a 4 and a 3 power, so 0 and 0. 3 or squared is right there. We're missing the x power, so that's going to be a 0. And then minus 14. So we have 2x to the 5th plus 0x to the 4th plus 0x cubed plus 3x squared plus 0x minus 14. Okay, and doing synthetic division, 2 times negative 4 is negative 8. Negative 8 times negative 4 is positive 32. Times negative 4 is negative 128. Negative 125 times negative 4 is 250. 500 times negative 4 is negative 2000. So negative 2014. So what I've shown here is that Q of negative 4 is negative 2014. And just to prove that, let's go ahead and calculate it the way we normally would. Negative 4 to the 5th power is 2 times 1024, negative 1024, plus 3 times 16 minus 14. Negative 2048 plus 48 minus 14 equals negative 2014. So we get the same thing no matter which way we did it, either using synthetic division or plugging it into the function and calculating using a calculator. Give it a try in number 8.